recording right now.
Oh yeah, but it's okay. What we're gonna do is we actually before we post, we actually edit out all these things, right? So don't worry about it. Yeah, of course, right?
Yes. Customer voice.
Yeah, I guess, but you are live on YouTube, so.
Okay, can you hear me now?
Yep.
Okay, so I'm gonna, if it's okay with you, I'll hold the questions to the end and I'll call on the students to ask their own questions. And I'm just gonna, so during your talk, I'm gonna just jot down who's asking what and the topics and try to group them consistently so we don't have too many repeats. And I'll give you I'll introduce you once we let everyone in and get started. Be very brief.
I guess it's time, huh? Okay.
We got about 160, 170. It's ticking up fast now, so.
Yeah.
And I'll ping the students who are doing the t-shirts, Jen, and then DM you during the seminar to make sure they're good to go.
Yep.
Perfect. So
I'm wearing the t-shirts.
Awesome.
All right. Awesome. I guess they all figured out the MIT time, so that's why we tell them to get to waiting room 5 minutes before, but they're all just showing up now. So.
You wait till we hit 300, Joel, and then let them in.
Yep. I'm minimize the number of times I have to admit from the waiting room. So.
Right, exactly.
We can remind them to try to join on time in the future. Yeah. Slowly, they've been joining late.
Yeah.
Well, I think the classes sometimes keep them long for lectures and projects too, a little bit, to be honest. So I'm watching some of the Discord channels and they're still scrolling.
Yeah. By the way, the related to talk today, more in-depth discussion is just published. So can share this to students.
Absolutely. I can just put that in the chat. What we'll do is we'll just copy and paste a few times. So yeah, that'd be good.
Where's the chat window? Somehow I can't see it.
Because you're on the full screen, right?
Yeah, but usually I still can find it. Somehow today I can. Oh, there you go. I'll throw in there. So
okay.
The IEEE spectrum.
Okay, that's great.
Yeah, so it's directly related, but the terminologies are completely separate. Okay. I actually don't talk about physical intelligence in that article because it's not quite established. But the gist is actually the same thing.
Here we go.
Okay. Hey everyone, welcome. Welcome back to your third week here at BWSI Summer Institute. Please put your name in the chat for attendance. Going to give it just a couple minutes for everybody to come in. Happy to see everyone back today. And I hope your projects are going well. So I'm going to get started. So today we have Professor Sang-Bae Kim, who is a professor of mechanical engineering at MIT, and he is the director of the Biomimetic Robotics Lab. He has a very impressive research history. He created the world's first directional adhesive and used it to create a climbing robot, and this was all inspired by geckos. Time magazine named him as one of the best inventions of 2006. Beyond this, he's developed the MIT Cheetah, which is another fascinating robot that can travel at very fast speeds. He has earned several recognitions, many Best Paper Awards. He was the recipient of the DARPA Young Faculty Award. He received an NSF Career Award and the Ruth and Joel Spina Award for Distinguished Teaching. So today he's going to talk about robots with physical intelligence. And so with that, please remember to put your questions in the chat. I will call on you at the end. It would be great if you can remember your questions, and I'll give you a prompt as to which question to ask if you've asked several. And with that, let me turn it over to Sang-Bae. Thank you so much for being here today.
Hi, thanks Jen, for introduction. This is Sang-Bae Kim. I'm a professor of mechanical engineering at MIT. I've been working at MIT about 12 years. Yeah, it's about 12 years now. And then my academic career is dedicated to robotics. So I know everybody's excited about robotics. So anybody excited about robotics? Raise your hand. Yay. And I'm how many people like animals? I'm actually a big fan of both. I'm interested in understanding how animal moves. Whoa, I see a lot of yellow hand. That's interesting. Why they put the hand color in yellow? I'm interested in biomechanics and biology and how animal works. And at the same time, I'm trying to compare that with our engineering disciplines and how we build the robot. So that's basically centered around my research. And I'll briefly show you what I've been working on the last 12 years. At the same time, I would like to throw you quite, how can I say, challenging questions. So might be topics you might work on in the future because it's quite far, looking far ahead. So the title is the robots with the physical intelligence. What is a physical intelligence? This is something I just made up about 4 years ago, and then the words by itself doesn't really mean properly because we actually don't have enough languages to describe these kind of things. So hopefully at the end of the talk, you have a little bit of better understanding what I mean by physical intelligence. Hopefully in the future, we have a better term. All right, let's start. As you know, most technology you are enjoying in your phones and your laptops and all kinds of technology you're enjoying are actually, if you really think about it, those are dealing with the information only. I'm seeing your face, and you can hear my voice. Those are all just exchanging information. And then we are living this amazing era where you can have a virtual seminar with the 300 people. It's amazing. Yes, sometimes it's on my hand. Actually, I can do this meeting with all my cell phone. So IT technology has been changing our lives. But at the same time, we also need a different kind of services. And then this kind of service I call physical services that actually need actual physical work. Labor, basically. So that's why I call physical intelligence. And then the intelligence they require to do this kind of service is very different from information services. So for example, delivery, you can't deliver item with the source of code using your cell phone. You actually need to generate energy. You have to pick up a box and then to move, going over some terrains and so on. Elderly care. This is probably the most important topic, especially for your generation. The world population is growing rapidly in a senior age group. And thanks to all these medical innovations, and our birth rate dropped very quickly. So in some future, and several decades later, we are going to face actual labor shortage. We're not talking about labor shortage on like construction or building products, because those are relatively automated. We're talking about physical service at home. Companionship, farming, construction, home security. You can think about all kinds of service work that you can just solve by just sending a code in your cell phone. You actually need a person or some automated machine. So that's what we're going to talk about today. And then it's actually quite underdeveloped. You might wonder, AI is taking over the world, and then soon it's going to be smarter than us. If you're talking about the left, maybe. If you're talking about the right side, the physical services, we're not even close. So I hope you pay attention well, and then they might shed some light on your future career. And another interesting thing about this physical services, it requires mobility. Cell phone you carry all the time, but any of these services you can solve by just buying stuck in the wall, because any of the physical services require mobility. So that's why I actually, start working on mobility. But anyway, let's think about what are the automated physical services we've been utilizing. These are the factory robots. This particular video is actually now a few years old. This is from BMW. It's pretty amazing. Like, you can lift the entire car chassis up and down, and with a sub-millimeter accuracy. These are really precise machine. They never get tired. Their repeatability is amazing. They do the same thing 1,000,000 times without failure. Somehow, if you go visit any factory, there are always people. It's seemingly a very easy job for us. Just plug in some soft cables. Yet, the current robots actually cannot. Robots are not capable of doing this. The reason, simple answer here, all these amazing robots that are in factories are purely following some position command. Go here, go there, open your jaw, and then close your jaw, and then move here, move here, there. There's actually no understanding of how hard this material is, how hard I can push, and so on. So when it comes to cable is a floppy. And then you don't know exactly where it is without having very high level precision camera and then very high end software. We are doing this all the time. I'm moving my hand all the time, but my accuracy of my hand is not even close to those robots. But we have a much better understanding of the world, and then I can grab things and then bend wire in a way that we want it. And then these robots actually don't have that kind of intelligence. So these are all alluded to the physical intelligence terminology I was talking about. We had an amazing competition called the DARPA Robotics Challenge. It's 2015. Now it's like 6 years ago. But technology didn't change that much. And then you're watching actually the most exciting part of the entire 5-day competition. And you might be wondering why these robots are so clumsy. They have amazing software there, a lot of programming, and brilliant engineers worked on it. The hardware on these robots actually are not that different from the hardware you saw in the previous robot in the factories, because that's what we know. That's why we're so familiar with. So still a lot of robots are built in a way that is the same way the manufacturing robots are built, where the precision is a top priority. I want to really accurately plug this in so we can assemble things well, but they can do 1,000,000 times well. That kind of characteristic doesn't really go well with moving around on the outside environment, outside the factory, where there's so much uncertainties. So I actually blame all these failure, mostly hardware. I blame hardware for these failures. So these robots are not designed to do physical interactions, like a colliding or absorbing energy by landing when you're landing. So if you think about animals, I mean, you can just watch yourself like standing up and down, walk around. But one of the extreme example, these are snow leopard chasing down mountain goat. Like sometimes the slope is like a 60 degree or 70 degree. And then they're not that accurate. These the animals are not a sub-millimeter, doesn't have a sub-millimeter accuracy, but they're really good at something. You know, when you watch sports and we're like a football player or basketball player or tennis player, you might think, oh, those are so accurate. compared to robots, we're not even close, but we're much better at balancing and then absorbing shock and then react on some unexpected event. So animals are built very, very differently from the manufacturing robot. So my career has been focusing on how can we change the robot design paradigm. I want to build a robot very different from this kind of robot in the factory because they cannot balance, they cannot apply forces. They are only they are the robot that does only the position, following the position command. So they're also mostly on the fixed on the ground, and then designed to work like this kind of picture, like just fix. And then when the car comes in, every position is known. Go there, weld, and come back. If you want to build a robot that operate in the field, that's not the case. We have to be able to move around, and then you have to be able to react on unexpected environment. You need to be able to balance because you have to walk around, and then you have to control the force rather than position. So I've been working on many different robots, thinking about these challenges, and I will show you a couple of examples. As Jen introduced, I actually worked on StickyBot, which is gecko-inspired climbing robot. This one actually had the world's first directional adhesive. I talk a lot of weird words, but this actually, the sticky part of the pad works only one direction. That's why I call it directional adhesive. We actually coined this term. The term didn't exist. This concept didn't exist. Well, actually exists only in biology. We just didn't know about it. So the sticky bar actually utilized that characteristic, and that's how it can actually climb up the wall without having trouble detaching the foot. Imagine you have a foot is very, very sticky, like a double-sided tape. You're going to have a hard time detaching a foot from the wall. But if you look at sticky bar, it's a very weak machine. Have no problem detaching the foot from the wall because the adhesive works only one direction. I love to talk about this about our hour, but there's other topics, so we'll move on. Yeah, this video is showing, you're going to see soon. There's going to be a little delay. There's a little hair structure that only works in one direction. In the real gecko case, those hairs are as small as about 100 nanometer. It's incredibly small. I also worked on cockroach-inspired running robot. This is a slow motion running on the treadmill. In the real speed, if you watch it, you don't understand what's going on. It's very fast. This is where I start getting interested in running robot and the running mechanics. Third robot I want to show you is probably the strangest robot I've ever built. It's called the mesh worm. It's an earthworm-inspired robot that uses the same peristaltic locomotion. Ironically, that's actually the same mechanism how you move your food inside your intestine. It's like a sequential squeezing motion that actually make things move forward. And I stopped working on it because it's so light and so weak, so I couldn't find a way to use it. It was a very interesting scientific project, but we move on to the cheetah robot, where you can actually move around in human environment. You can climb upstairs, and you can actually do some physical work. So this is a cheetah 1. At the time, our controller wasn't very great, so robot has to be able to help. We have actually hold a robot in plane, but we will be able to test a lot of motor characteristics, how fast does it need to be, how powerful it has to be, and how energy efficient it is. It turns out that this robot was as efficient as an animal. So that was very promising, and then they allow us to develop next generations. So I'll show you those in the next slide. Oh, after this. So the key idea to make robot that moves around and then being dynamic is being able to absorb shock. Compared to the robot you saw in the previous videos in the factories, those are very, very rigid and then cannot handle a shock. The details are a lot more complex. I hope you can come to MIT or go to the college and then learn more about robotics. But the building robot that can absorb shock in this kind of high-speed motion wasn't very common. It wasn't very straightforward before we actually introduced this kind of concept. We're not actually the first one who used this concept. There's other community, like the haptic community was using it, but we actually used for the leg robot. So that kind of characteristic actually allow us to build a robot like this. This is a Cheetah 2 that actually fastest robot we ever built. It actually ran up to 6 meters per second. It's slightly faster than your jogging speed. Still not as fast as a real animal. You know, your cat or dog can be faster than this robot. But by the time there's no robot, especially powered by electricity, was be able to run like this. And this is probably the only one where we're the only one who did this, like a steeplechase. Robot actually see the obstacle autonomously, change the step, and then jump over obstacle and then land stably. So you see the little black sensor in front of the robot, which is called the LiDAR. You probably heard about it if you read about like autonomous car and stuff. So it's a laser sensor that detect the obstacles. This is Cheetah 3. Robots are getting a little uglier because it's a lot less bio-inspired, but it's actually more functional. It become more versatile. So our design evolve toward in a more robotic way, and then you can achieve more robust, more versatile functionality. This robot will be able to climb upstairs without vision. This is all blind operation. It's not that I want to climb up blindly, but we don't want to rely on camera only. We want to have some redundancy. That's why we're testing the algorithm. And thanks to our custom developed electric motor, this robot is very powerful. The last robot I would like to show you is a mini Cheetah. This is probably the most dynamic and then most robust robot we ever built. Thanks to its size, this robot is almost indestructible. This is the first version we built, and then running in our lab for 2 years, we never had any mechanical failure. And a lot of people think it's cute. We actually bring this robot to the Jimmy Fallon show. You can look it up, Jimmy Fallon show, and then we actually demonstrate in front of Jimmy Fallon. That was one of the showbotics issue in 2018 or 19. I don't exactly remember. Our software getting better and better. So our software has become more versatile. So we can apply many different gates. And we can handle very large disturbances. So balance is actually the center part of our research so far. And then being able to balance while walking is actually very, very important, and then it's been difficult. Now we're showing off all kinds of behaviors because thanks to our software development. And then we're showing some extreme behavior that no other robot could show, because our robots are actually built for that. We're not building something that precise and slow motion. We're actually built robot that can drop from the meter height, from shoulder height, and still absorb shock, and then still stabilize it. If you drop a robot based on the manufacturing robot, as soon as it hit the ground, it's going to break its gearbox. It's going to break all kinds of parts. But our robots are not built that way. That's what I mean by the paradigm shift. We want to change how robots are built in a way that this kind of mobile robot can be useful in our life. And so far, it doesn't have a camera, but still doesn't fall because it's an excellent balance controller. So you're going to learn that the building hardware is important, but the software eventually is going to determine the performance of the robot. So now we have a camera. This is also a few years back. We have a depth sensor. It's a camera that can see the 3D. And then robots are automatically choosing its step so that it doesn't topple over this obstacle. You can avoid the obstacle, but also it chooses the right location. And the obstacle is too high to walk over, we can jump over. So if you see the left top corner, you can see the blue or green. And blues are the not good location to step on. And then greens are more flat. So those are good places to step on. So robots are automatically look at the 3D map and then decide where to move your foot. And then the red dots are the parts robots are seeing now. But the robot has a good memory, so it look at around and then it build a map, and then it memorize where it is. So even though you're not looking at the obstacle right under your feet, you still remember where the obstacle was. You can still make a decision. Like you climbing up the stairs. When you climb upstairs, you're not looking at your foot all the time. You're looking at your friends and then saying hi, but somehow you don't trip because you remember where the step was, and then your legs kind of know where to step. The key idea is actually making the electric motor properly and very high bandwidth. You're going to learn about bandwidth when you go to college, but the easy term is a fast reaction. I mean, the factory robots wasn't fast. The factory robots are really fast too, but they don't react fast. If you hammer or touch it, they are pretty much like moving sculpture, cannot absorb energy. And then, whereas our robots are built such a special way, we built our own custom motor. We actually need to wind our coil, the first motors, and develop our electronics from scratch. And then now our robot can react so fast, we can control the force within like a blink of an eye time. So if you look at the history, this is very rough summary of leg robots. 2001, the Shimo. And if you look at the robots are below the bar, these are all hydraulic robots. A lot of them are Boston Dynamics, but some are from other robots. And then initially, hydraulic robots are really popular because hydraulics are very good at handling shocks. Excavators and then bulldozers, those are actually built for digging ground, handling shocks and impact. So it's very good for leg robot. But its energy efficiency was really, really bad, and then very hard to control and build well. So in the beginning, hydraulic machines are all dominating until MIT Shira show up. The red rectangulars are all our robots, and then people realize, oh, electric motor actually can be really good. And then ever since 2016, there's no hydraulic quadruped exists, only humanoid. You probably know the Atlas, but everybody else start working on electric quadruped, which is pretty much copy from our robot. So this is in my opinion, pretty good achievement. I changed how robots built and then show how electric power can be very powerful and then very good. Electric machines are actually a lot more fast response, and it can be very, very powerful. I will show you some of the more recent update. Our controller will be able to jump a lot more diverse way. You can see the obstacle autonomously just jump over. And it's not only jumping forward, it's actually jump to the diagonal direction, to the side. Our softwares are getting more generalized, so we can actually code many different behavior much more easily. Before, we had to write code for every specific behavior. Now we can write a code for a group of behaviors. So that's progress. So you're going to learn about software later. It's very cumbersome to write every behavior. And then, because whenever you want to do something new, you have to rewrite the code. But we're actually getting better and better at writing code that can do many different things. I'll show you a different type of jumping. For example, let me show this part. Spin, you can jump and spin mixed together. So these are all coded in the same way. So you can specify how much you want to spin, which direction you want to jump, and specify it, and the robot figure out how to do it. So you can see just jumping and turning, or jumping and rolling. So those are all automatically coded. So I don't need to write code for each behaviors. So now is ready to connect with the camera and then let the robot figure out where to go, and then jumping and mixing jumping and running and so on. And I want to show you briefly how robot actually figure out where to go. And if you see the leftmost picture, robot camera will see the map, this 3D map. And then they figure out which part is more flat. They classify it. This is a flat, this is the obstacle I don't want to go, this is possibly a place I can step on, and so on. And then create a trajectory, the third picture. This is a goal, this is where I am, and draw a line straight first. But they soon realize robot want to have some safety margin. So we modify the trajectory to be more safe. And then you create, based on that trajectory, you create that kind of a safety boundary. So we're doing this kind of like a trajectory planning in real time. So even though robots see something unexpected, it can adjust its trajectory right away. So I'll show you that quickly. So this picture is demonstrating, this video is demonstrating the goal is behind the box, the Pelican case, and still know where to go. And then robot has to turn to see the goal location because this is an unseen environment. So robot has to be able to adapt. And next video is like human students are actually jumping in. He's actually undergrad, so we'll see. Walking, he jump in the middle, and the robot automatically notice and then turn around. It's a little bit slow, but we can tune to make it robot faster soon. And you'll see how happy our student is. So he's undergrad, so he's been working on our lab for many years, and really happy to see this autonomous behavior by his code. I want to briefly talk about teleoperation. So far, you've seen a lot of development of the leg robot moving around, jumping over obstacles, and so on. But when it comes to moving hands, as I said in the beginning, the physical intelligence is not there yet. So we're thinking about using some human intelligence for now. So this is a teleoperation demo done in our lab. You can't quite feel the things I'm feeling, but I'm actually feeling the force that the left robot is feeling. So right robot, you see my hand is manipulating my left robot just through the wire. So these are not physically connected, it's all through the program. But I can actually feel the force. Not only I can control the robot. So if you develop this kind of technology in the future, we can possibly provide some services. I'll skip the detail. This is actually a contact sensor we were developing. And thanks to our develop fast robot arm and our contact sensor, we can do this kind of magic demo. We call that as a virtual magnet. Obviously the wood wouldn't get attracted to rubber, but this is all programmed. Once the technologies are developed far enough, you can distinguish from the magic, or you might heard something like that, right? We write a program in a way that rubbers are attracted to wood. But these are all force feedback controlled system that we developed and then write a code. And this is not easy to achieve because you need a very special force sensor, and you need a very special robotic arm. Those are all developed by our labs. So at this point, we're the only group in the world can demonstrate something like this. So soon our robot will have a very good sensor in the tip, so it can be a lot more sensitive and then reactive. I want to show you one quick demonstration of apple picking, but possibly boringly, this is actually done by me. So I'll show you. Did you see that? I'll show you one more time. That was pretty quick. Have you seen it? There's some delay. Me picking an apple. I'll show you just one more time because there's going to be some delay. So that's a picking an apple. Everybody can do it, right? But have you seen your hand, what your hand is doing? If you see step by step, it's pretty remarkable. First of all, I was picking an apple blindly. I'm not actually looking. I'm just like reaching out to the ball and then picking an apple. So my hand just collide with the apple. And you can see that if you write on code, if you know everything, you probably want to pick an apple that the hand touches, the top two probably. But somehow my hand just tried to grab right away. Hit something, try to grasp. And then it turns out that I happen to touch more apples than two. I happen to touch like 5 apples. And somehow choose to grab something the hardest. This is not happening all the time, but it happens sometimes. And then you realize there's a lot of apple piled up, so I need to move my hand, digging in more to grasp that apple. Let's go in deeper and then bring it out. It is pretty successful grasp, but if you take a look at individual decision making, it's pretty dumb. It's not very smart. My hands are not very smart. I'm blaming. Look at me. I'm blaming my hand, not blaming me. But I claim that that's a fair enough because I actually didn't know what my hand is doing. Try it. If you try to pick up any object in your hand in the front of your desk, and then seems like you're controlling every bit of your hand. Yes, I'm controlling every bit of my finger. But when you do something, just bring out a keychain from your pocket. Try something like that. Do you remember any action you did by doing it? The bottom line is you're sitting in the chairman's chair in the company. You're like sitting in the CEO's chair and then ask your company, oh, develop a product. And then something magically happened. And your fingers are doing a lot of little detail work. There's a complicated algorithm going on. We don't even know quite. And then suddenly done, so I don't care about it. But there's a lot of detail, complex behavior happening. And not all of them are not necessarily optimal. You're going to learn about optimal control later. I mean, you see my behavior of picking an apple. Individual actions are not very good, yet overall performance is pretty robust because there's some common sense going on. We are not even close to write programming code for robotics yet. Not even a single behavior like this. Every robot is still very clumsy and very quiet. This is things I'm talking about physical intelligence. Like peanut butter jelly sandwich. Anybody can learn and then write a make a peanut butter sandwich. Just spread the peanut butter on the bread. How difficult is that? Just think about the word spread is a very, very vague word, a very abstract. If you think about write a code for robotic system to do this, we have absolutely no clue. So a lot of actions and a lot of language we're using are not quite programming ready. That's exactly what's going on in the physical world. It's not really true in the digital world where the information is moving in the exchange. We're very well defined. Our pictures are defined by pixels. Our voices are defined by the data, voice data. When it comes to physical actions and forces and bendings and squeezing, you don't even have proper language. You cannot easily digitize this and then communicate with the computer. That's why you don't see a robot doing some dishwashing. This is probably one of the extreme version of dishwashing. In the restaurant, you have to wash really quickly. This is unbelievable how quickly human can do. Again, you have to see the slow motion to see any detail action and what it does. And you're gonna soon realize he never even have a second is holding the tray. It's almost like a skiing around the tray. Two hands are like skimming and sliding, and somehow it kind of like rub on almost every surface within a second or two. And how would you even write a code? Because their positions are not defined, forces are not defined. Humans are following some abstract concept to achieve something like a cleaning tray. Cleaning tray is very vague. So in order to really write a robot to do this kind of stuff, we need to be able to write languages, not only human language, also robotic languages, to translate this to computer world, which we're not lacking. We're not having it at all. You probably think about program that can beat like human chess player or Go player. Wow, that's amazing intelligence. But you don't think about writing a code for picking out a keychain from your pocket. You don't think that's intelligence because that's a small kids can do it. Some animal can do it. But that might be wrong because the level of intelligence in this area, are very self-conscious for you. When you do movement of each chess movement, you have to think about every action. When you grab up keychain from your pocket, these are completely unconscious part of it, subconscious part of it. And then we tend to underestimate them. So bottom line is we as a human tend to judge the level of difficulties of certain tasks based on what we are good at, which is very, very different from what the robots are good at. So I want you to think about this kind of stuff. And then if you want to learn more about, there's actually an article I wrote and just published this today in IEEE Spectrum. So you can find in the chat window. and then you're going to have a better understanding what I'm talking about. So to summarize, because times are already 1:10. First, Lego robots are becoming more important. It can be used for a lot of autonomous tasks. You see, the moving around is getting better and better. And then the actuation, the development of electric motors that geared towards Lego robot was very important to make this kind of robot possible, and then very diverse, versatile. But the physical skills, the hand skill, are heavily rely on the subconscious action. So you don't really understand. You don't even quite remember even. So in order to build the robot like that, we need to understand how human is doing, partially probably, but also we need to be able to write a code that can understand this very abstract action, not just like controlling X, Y, Z, move here 10 centimeter, move forward 20 centimeter. That kind of control programming is not going to help us to build a robot that can do the dishwashing or even cleaning the house. So it might be very confusing, but I want you to start thinking about any actions you're doing by hand, and then think about how much do you actually remember, how much do you actually recognize. You might be surprised how little you're actually involved on your side of the story, your side of controlling hand. And then when it comes to robotics, that part, the subconscious part, the hand skills are very underdeveloped. We're far from achieving this kind of task. So with that, I would like to finish my talk, and then we'll move on to the Q&A. So thank you for your attention, and then let's talk about any more detail, if you have any.
All right, thank you. We have a whole bunch of questions. Maybe we'll start with Zachary. He had a question on how to prepare for a career that you're pursuing.
Yeah, hi. So I was just wondering, like, what you would recommend studying in college for someone who wants to do robotics, kind of like you have.
Good question. I think I cannot overemphasize the importance of the coding. So the programming and coding is becoming like a language. It is called a language, and then it's like a English speaking. When you're younger, you learn how to read. Oh, reading is so important because that's how you communicate from people who wrote knowledge on the book. And programming, I'm not actually a very good programmer because I grew up in the different era. I was a mechanical engineer, and my students are doing most of programming right nowadays. But it's becoming like a very essential language. So if you don't write program, you lack of this communication skill. You don't necessarily need to be the best programmer in the world, but this is, you don't need to be the best speaker. You don't need to be, like Obama, like you don't need to be the best speaker in the world, but you need to speak languages you can communicate with people. So that's pretty much the coding and the programming skill you need to have. And it's a language, so it's earlier the better. So I encourage you to just jump into programming as a hobby. It's like exercise, I need to prepare for the future. It's like a muscle. Other than that, I want you to really start thinking about physics. Physics is something also takes quite a long time to get used to. I mean, physics lecture might be boring. It depends on teacher, but physics are fantastic. Physics are, phenomena are happening in your world, and then understanding it. If you don't quite understand physics as a concept, no matter how good you are in programming, you can't write a code for robotics because your robots are doing physical actions. If you want to just write a code for a computer, cell phones, and a laptop, fine. You don't need to understand physics. But I think those areas are very well developed. By the time you guys grow up and getting a job, I think that kind of actions, the worlds are already light ahead of you. The things I'm talking about today is though a chance to really make a difference. And then that's where the technologies are very lacking. And then I talk about a few reasons why these are underdeveloped. First of all, we don't quite understand. In order to understand, you need to understand the physics. The machine learning actually allows us to do these things without understanding physics. So some of the things are probably we need to rely on machine learning without understanding physics. But I still think actually human understanding writing code is actually a very dangerous idea. You've probably seen many examples. I can talk about it if you have any specific example. So I would say physics, programming.
All right, thank you.
Well, I cannot miss out math because mathematics are a type of language. So, that's just obvious. I trust that everybody already know math is important. That you probably heard so many times. So I just skip that.
Okay, so that's great. Ashita, you have a question on how this involves, this research involves other disciplines?
Yeah, so I was wondering that, like, you mentioned that there was like you were looking after animals for your inspiration. So I was wondering how much of your work intersected with fields like zoology and biology, and did you learn anything from those scientists, which is like kind of a different mindset than engineering, and like
Yes.
apply those insights?
The different mindset, that was actually a really important word. You picked the right word. So I was the one who, like, promoting, like, learn from animal. There's a gajillions of like billions of years of knowledge accumulated. We just need to discover. It turns out that applying those knowledge directly to engineering world was very difficult. It's not that I never had it. I had a few successful example, but the amount of time you invested in the biology, the things you can utilize in engineering world is becoming the investment return is not very good. But that could be actually wrong because of the mindset you just talked about. If I look at individual things, if I study muscle, if I know everything about human muscle, can I build a better actuator? The chances are very slim. But if you study and understand biology better, your mindset and perspective is completely changed. So it's hard to even describe because the things I feel in change in my brain is very abstract level. Like, I actually became a lot more humble. First of all, more I study about biology, I became a lot more humble. What I mean by humble as an engineer is like there are some group of people who doesn't study biology. They think the mathematics and then the physics or programming they learn. Many people are more like an anchor to the mathematics, and then they think that's the world, that's everything. And then that's very narrow-minded and very dangerous mindset. Once you start studying biology, and then you soon realize, oh, this mathematics is a very small fraction of the things that can describe the world, because the mathematics is what human created. Yes, it's a great tool, and then but it's very narrow point of view perspective. It's a language that describes how the world works, but the mathematics that can describe only a fraction of what's going on in the world. That's why I think the studying biology actually allow you to see the world completely differently. I think make you see the world in a much wider perspective. So I'm glad that you talked about this, and so that's why I still think it's worth studying biology, even though they are night and day sometimes, many times. It really changes how you see things differently, and then make your brain more flexible. That might be easiest way to think about. Make your brain a lot more flexible, and then make you more wide thinker, like not narrow-minded.
Yeah, thank you so much. I'll definitely keep that in mind as I
Yes.
go through my engineering career.
Okay, let's see. Amanda, you had a question about AI and reinforcement learning?
Okay. Give me 1 second. This chat has so many messages. Also, I think we might have to do the same thing as last time where someone else goes before me.
Sure thing. Ethan, you had a question about bipeds versus quadrupeds.
Yeah, so I've seen many robots that are bipedal, and I'm just wondering what benefit do we get on researching bipedal robots over quadrupedal robots? Because it seems like it would just be a lot harder to get to work and balance and whatnot.
You're absolutely right. And then this is actually the question I got when I was interviewing for MIT professor job. And then I was completely fumbled because it was first of all, it's a very difficult question to think about. And then this has been debated over in academia over many decades. And so my answer might not be simple, but you're absolutely right. The biped is a lot more difficult to balance because you have just two legs. And if you look at the biology there, right? There are only a handful of animals are biped, like a bunch of birds who, I mean, most birds can walk on biped, but they're not the best biped. But there are ostriches, for example, they never fly. So, and then human. And then the most of other animals are actually quadruped. And then we believe that there's a reason behind there. Quadrupeds are a lot easier, a lot more versatile. It actually can be more agile. Yet, if you think about why human evolved to be biped, and then I believe that it free up the hands. So now you can actually run with the spear and then throw at it instead of you have to chase down and then you have to bite or scratch. That's a completely different level of your skill. So if you think about, that's a biological perspective, but if you think about our world, a human, like a service robot in the human world, similar problem happened. Quadrupeds are fantastic moving around. It's so much easier to build and then build a robot controller stable. But in order to reach something, because we want the robot to service in our own environment. I have something in the kitchen cabinet or even bookshelf. I want to reach something. And the quadruped has to be quite massive to attach another arm to reach bookshelf. Whereas a humanoid can be much narrower, much smaller, much lighter, still can reach high. Just think about yourself and compare with the biggest dog you ever seen, Malamute or Siberian Husky. They had a hard time reaching anything because they're almost as heavy as us. So same thing happened in robotics too. But you don't want the robot to be too big that's servicing in our house. So, and another challenge like going in a narrow space, four-legged animal cannot fit in small space. Human can be fit in very small space because we're upright. Of course, there's challenges, but so that kind of like pros and cons are happening in between biped and quadruped. So still under debating like what is better form factor for future robot. Who knows? We don't know. 3-leg. We don't need to stick on the animal, all right?
Thank you.
Hey, Amanda, are you ready?
Yep. So hello, Mr. Kim. It's very nice to meet you. My question was, how often do you use AI and reinforcement learning in training the robot to do tasks, assuming you use them at all?
So we use very minimally so far. And honestly, I've been, for a while, a few years, been skeptical about physical, like a dynamic work. But apparently, machine learning can actually do a lot of those, even like balancing and climbing stairs kind of thing can be done by machine learning itself. We actually use machine learning for much smaller tasks like mapping some sensor. The force sensor I briefly show you actually use a training by machine learning to supervised learning to do that. There's actually reinforcement learning and supervised learning is very different. There's a lot more different terminology. We all call this as machine learning, and AI is a lot more vague terminology. But the machine, if you say machine learning, that automatically means you're using data training, as you said. We're relying on training rather than hand coding. It actually can do things much better and easier, faster way than compared to what we've been doing. That's kind of like a loophole you can fall into if you just fall in love with the mathematics only. Because sometimes the mathematical formulation is not the best way to represent certain phenomena. It's a kind of detour. Whereas machine learning, neural network can just connect much more intuitively quickly. The problem of machine learning, though, is we cannot quite understand the neural network is formed. We can manipulate the data. We can manipulate what kind of algorithm we're using to form a neural network, but we cannot directly control the thinking of that neural network. It's a reflex. But so if you throw too many tasks in the one neural network, it's going to be very difficult to tune in the right direction. So that's why, I think it's better to keep this neural network or machine learning to be relatively isolated task. when it comes to more complex tasks, we have to do this at the same time, do this, and then you want to fine tune all these so that we can, for example, keep it safe or and so on. That's where you might want to write a code differently, so you can actually tune this parameter properly. Because if you write a more traditional way, you can actually tune the parameter in real time. You can see in a second or a half second. In the machine learning, if you change it, you have to retrain the whole thing. So you might have to wait at least a couple of hours, sometimes a couple of days to see what your change is. So it's going to be very difficult to move toward a certain direction. So that kind of debate is still going on, and then still answers are changing. The people's perspective change and so on. So we'll see. But so far, we don't quite understand how the machine learning is doing the abstraction. So still the academia is cut in half. Like some halves are believing machine learning is going to change the world. The other half is still being skeptical. And people like me, I think it's going to be some hybrid, some mixture of the mathematics-driven, modeling-based driven code coupled with the machine learning.
Thank you. That was very insightful.
Okay, so maybe one last question. KG, do you had a question about some of the future applications?
Yes, thank you. Oh, thank you for the amazing presentation. I was wondering, what do you think are the most exciting applications of physical intelligent robots?
The things I talked about, construction and then farming, delivery, but a lot of people want the robot to clean their room because we're lazy. I don't think that's actually most exciting in my opinion, because I think we should be more physically active. But elderly care is a different story. I'm mostly excited about the elderly care. There's a lot of little things, like even the vacuuming on the floor or organizing things, delivering a cup of water. Some the elderly population, they cannot even move. They have some spine issues, some leg issue, and then once you lose that mobility, you absolutely need some physical service. But think about every person who has some mobility issue. You have somebody living in the house to provide service. It's not going to be very useful. So we want to have some robotic agent to help something, and then possibly teleoperate by somebody else through the internet. But that person cannot control every single detailed action through the internet. So the robot need to have some good physical intelligence. They can do manual work, and the human is only making high-level decision. Okay, let's go to the refrigerator to get a cup of water. Cup is from here, refrigerator, or the water from here, things like that. But the handling the object, I think, has to be done by robot by itself, because the internet has a limited bandwidth too.
Okay, I lied. One more question, if we can just sneak one more in. Grace, you had a question on the design process.
Oh yeah. So hi. First off, thank you for your talk, and it was like super interesting and insightful. And I guess like for a bit of context in my question, I'm in the assistive tech course, and we kind of focus more on designing the product for our co-designers to help alleviate some of the issues they may face with completing certain tasks. So in particular, I was wondering how your design process looks like and with these like robots, and how do you get started with these projects? And I guess like how does your timeline look like with such large scale projects?
Honestly, I have to confess that if I look at how I developed robots, the process was missing. I actually want to enforce more process. I'm actually teaching a class that does this. It's called the 2007. It's a over 30-year-old, very famous, long-lasting class that teach you how to design process. Robotics. The problem of robotics is we are designing something always very different from the previous one. So it's very hard to apply some design process. If I really show you like a performance graph over time, it's more like this. Nothing happened for 6 months. And then on one revolution or one good conversation, 1 week, amazing work, and then nothing happened. And then at some point you have to make a decision. Should I just build, or should I just wait another 6 months? Hopefully something happened to my brain. that kind of thing happen a lot. We're actually designing humanoid right now, and I've been designing really fast during pandemic for 3 months, and then I got stuck on something. I didn't even know sometimes what I'm stuck with, and then I didn't do anything for 4 months, 5 months, and then at some point it fall into this like same patterns of brain. I look at the parts, and then my brain goes same way, so never improve anything. So at some point, I grab my students like, okay, I'm done. You design it now, and then he bring his a completely different, fresh perspective. Even though he's seen what I'm designing, it's a very different mindset if you actually take ownership. And then he actually improved quite a bit, and then make changes that I couldn't make changes. So it's a very interesting. Like it's very difficult to have a co-design, like 3 people meet together all the time design. That doesn't necessarily work. And then, oh, you design arm, I design leg, I design body. That also not necessarily wasn't work well. I think sometimes you have to actually, I design scratch and then toss somebody, you design, and then toss back and forth, or third person. Because the especially robot design is very difficult because there's a lot of moving parts, which is very different from designing a table. Even a car, car has only 2 degree of freedom. So everything else is pretty much like a structural design. Robotics are crazy complex. They're like a 10 degree freedom. And then there's a lot of way to reroute to even wire. So it's been pretty difficult to apply design process. But I think, I confess that we need to have a more processes. And then maybe next year, if you see me again, I might have a better answer. Let's put it that way.
Thank you.
Okay, Sungbae, thank you so much for being here today. At this time, I'd like to ask Kitty and Andreas to unmute your mics and present our speaker with a little thank you.
Sure. So thank you so much, Professor Kim, for presenting to us today about your really fascinating work with biomimetic robotics and also dynamic physical intelligence. Personally, I've always enjoyed watching YouTube videos featuring the MIT cheetah robots, and I'm sure many of my peers share the same sentiments. So learning a bit more about the logistics of just shock absorption, proprioceptive force control, and mobility behind this field of robotics today has just been really incredibly enlightening. So as a token of our appreciation and gratitude, we would just like to present you with a virtual BWSI t-shirt.
Yay! Thank you. Thank you for your. Actually, I already received it, so I'm already wearing it.
Oh.
Thank you, Bob. Give it back to me. Yep.
Great. Thank you so much. And students, we will see you tomorrow for our next installment of the seminar. And Sungbae, thanks again so much. This was a really.
Thank you. It was wonderful.
Thank you.
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 Thank you.